Let's take a few moments to ponder a little bit of history before we get into the main ideas of this video. This man here, Johannes Kepler, lived a little before, a little bit after the year 1600. And it's amazing what he was able to pull together using this instrument here, something called a sextant, where you basically just a glorified protractor to look at the stars and the planets. Really poor methods of timekeeping. That's all they had to track the motions of the planets. And with virtually no mathematical tools or anything, he was able to come up with the following 3 laws. Now we're going to go through these 3 laws in more detail. If you'd like to pause and read through them, you certainly can. But just try to keep in mind the whole time of all that he was able to pull together mathematically without real strong mathematical tools of the time. Kepler's first law made the connection between the motion of the planets and an elliptical path. So it seemed as though things were moving in a circular path, but in fact he was able to deduce from the data that they actually move in an elliptical path around the sun. And the sun is at what we call the focus of the ellipse. Here's a diagram of an ellipse, and you can see F1 and F2 labeled there. Those are the foci, each is a focus. They define the shape of the ellipse. As they are moved closer to each other, the ellipse becomes more like a circle, and if you move them further away from each other, the ellipse becomes flatter. And so by taking some measurements about the shape of an ellipse, you can describe how circular or non-circular it is. Our circular orbit that we've talked about is really just a special case of an elliptical orbit. Just in case you're interested, there is some terminology that's used when we talk about these elliptical orbits. We refer to the major axis as being along this long direction, and the minor axis along this direction, just having to do with which is longer than the other. But the key term that I'd like to talk just a little bit about is this, eccentricity, which is the ratio between what's called C and A. Here's C and here's A. So the smaller that C is, the closer that the focus is to the center, and the more circular this is. If E equals exactly 0, then you have a circle. So what about our planets? How elliptical are the orbits? Well, it turns out they're not very elliptical at all. Earth is very typical for the planets in our solar system. The eccentricity is only 0.017, so it is basically a circle. With the naked eye, you cannot tell the difference between a circle and this ellipse. Again, that means that the sun is really at the center of our orbital path because the 2 foci are basically at the same spot. Mercury is one of the more elliptical paths, but even that is only 0.21. And if you were to look at this picture down here that shows the path of Mercury to some accuracy, I don't think you'd be able to tell it was not a circle. The only difference is that it doesn't have the sun right at its center. Okay, so that's where they can sort of determine that or where that comes from. Other bodies in our solar system and beyond, it's a little bit more drastic. So this would be the path of Halley's Comet, which is something that comes around every 76 years. It really is orbiting along this elliptical path. It's just that we can only see it when it is over here near our sun. When it's over on this side of its path, this far away from our sun, we just don't see it at all. And so that would be a very drastic ellipse. Meteoroids and other bodies follow other paths. They can be parabolic, they can be hyperbolic, where they never actually return back to the same spot. Now, although the first law is interesting, it doesn't really give us anything to base a lot of our ideas off of. It really just sets the stage for the ellipse idea rather than the circular idea. But even though it is, even though, say, the Earth's path is nearly circular, it is slightly elliptical, and so certain properties can be observed. Kepler's second law was originally stated this way, that if you imagine a radius from the sun to one of the planets, and imagine how that sort of moves around on that elliptical path, there would be an area, shown here as a shaded area, that is sort of swept out. That's the phrase that's used. And if you were to compare the swept out area in 1 month versus another month, equal amounts of time, the areas are actually the same. So the shapes are different, but the value of the area would be exactly the same. Now, in terms of trying to connect that with something mathematical, it is kind of hard to do. But the key thing is that means that the planet actually moves faster at certain points in its motion. So in this section over here, in this part of the picture, the object is actually moving, or the planet is actually moving faster. It travels faster compared to this spot over here. And so we can kind of build off of that using the ideas of angular momentum. Angular momentum is conserved if there is no external torque, which would be the case in this situation. All of the forces that are causing rotation and so forth are all internal. They're mutual between the sun and the planet. And so there would be no external torque, so angular momentum would be conserved. There's no change in the angular momentum. Recall that angular momentum for a particle is r cross p, or r times mv times the sine of the angle between r and v. Writing that all out, we get this long statement here. And it can get a little bit messy, but if we focus on 2 particular points, it actually simplifies quite a bit. We're going to focus on the point where the planet is closest to the sun. This is something called the perihelion, and the point where the planet is furthest from the sun, the aphelion. These are not terms you need to memorize. Again, just some people are interested in those sorts of ideas. But the idea here that we focus on when it is closest to the sun, why that's useful is because the velocity is exactly perpendicular to the r. And that way we don't have to worry about the sine portion. And the same thing over on the other side, our velocity is perpendicular to r. But what we're saying here is that at this perihelion, we're going to have a much greater velocity to correspond with this smaller r, whereas the aphelion will have a lower velocity corresponding with the bigger r. And this is going to be the key idea. You can jot that down if you want, or we'll summarize at the end of the video. The third law is actually something we have talked about before. We derived it in the last couple of days in class. The square of the period is proportional to the cube of, we had just said the radius, and now it's the semi-major axis. So we basically have the same formula we derived in class and in a previous video. It's just that instead of using r, we are using a. And I've chose to write this the way it is more traditionally written, where it's t squared instead of actually solving for t. And what's kind of neat about this is you can compare the periods and the positions of all of the planets, and you can see a linear connection between the time squared and the position or distance from the sun cubed. All right, so in summary, these are sort of the key ideas to know. They are not formal ideas that are written on the formula sheet. So again, ideas to understand that the angular momentum would be conserved along an elliptical path. And if we focus specifically at points along the major axes, the masses cancel, the sine of theta cancels out, and so we get this relationship here. And then what we have derived before about the period of a circular path can be adjusted, where we just use the this value a, which is half the longest axis, instead. You may want to think about it in terms of this as well, as sort of a comparison of these sort of squared and cubed ratios.